All right. So my day is a bit fragmented today. I have a appointment in the morning in about an hour and a half, and then I have another thing going on this evening. But I want to get in the habit of, instead of just like not streaming on days where my day is like super fragmented, to actually just get some hours in. Um, yeah, so I'm gonna do that. Um, we're discussing Omba's law previously, and I guess one thing it's top of mind for me. I just want to get out to learn log uh, problem sets, and we'll say down here I want to say projects as well. Projects active is epoll. I guess I can lowercase that epoll file HTTP file server. Just want to get it on the map here. Before I move on, because I'm getting in this habit of kind of like lack of focus on my projects. So I have the epoll file server, and then let me link this bad boy up here. Epoll file server, boom. So here we go. Cipher 0 dev. Okay, that's good. Yeah, I think my focus is like drifting because I want to focus on this book and do all the exercises and problems for the book. I feel like that's like a good next step for my learning, but I also don't want to like leave these projects abandoned. I did a lot of work on the epoll file server, fleshing out the initial idea. I still have to implement HTTP, and I still need to write a bunch of benchmarks or use Apache benchmark or Siege or something like that to actually do some benchmarking on its performance relative to things like Nginx or other web servers. There's still some large amount of work that needs to be done on the project. Not a large amount, but there's still some work to be done on the project. So that's like one project idea. That I want to actually get completed. I guess this whole thing I can just delete there. The other thing, toy shell. Learning objective would be to get more experience with fork clone pipe. We'll just say clone pipe. Exec v. And we'll just say here K. Computer systems, a programmer's perspective, has a lab for this, so I might do this as part of that lab. Toy shell, memory allocators. I already implemented a basic free list allocator as part using sbrick as part of reading KNR. This would be a repo to implement other allocation strategies, more modern allocation strategies. I'll just leave it like that. Um, forget how to spell that. I'm just dumping all my ideas into this doc. Okay, I think that's probably everything that's been on my mind recently. Um, Add section for projects. Okay. So that'll avoid having some of these things turn into vaporware. Um, I mean, the ePOL file server, I'm still. At least it's in a buildable. It builds. It does something, but it doesn't do the thing that I need it to do. Um, oh, I guess. Build a HTTP file server. HTTP file server based on IOU ring. So we got books, documentation, courseware. Okay. Well, let's dive into this. Actually, you know what? I'm gonna take a quick break, and then so it's 9 o'clock. I have to be at my appointment at 10. We'll take a quick break, just bio break, and then we'll do about 30 minutes of reading on these practice problems and maybe make some progress on that. But I do need to break at least 9:30 to go to the dentist. So yeah, I'm gonna take a quick break, and then I'll be back to do a little bit more work on these problem sets. All right, be right back. Oh, wrong button. All right, I am back. So I'll go ahead and tear this down. Oops. This little browser here. All right, so we are at the end of Amdahl's law discussion here. Practice problem 1-1. Suppose you work as a truck driver and you have been hired to carry a load of potatoes from Boise, Idaho to Minneapolis, Minnesota. Total distance is 2,500 kilometers. You estimate that you can average 100 kilometers per hour driving within the speed limits, requiring a total of 25 hours for the trip. You hear on the news that Montana has just abolished its speed limit, which constitutes 1,500 kilometers of the trip. Your truck can travel at 150 kilometers per hour. What will your speed up for the? So this is applying Amdahl's law. Okay, let's go ahead and maybe jump over to CS app. And we'll go under chapter 1, problem. So they call these practice problems, and then at the end of the chapter there is let's find chapter 2. Is it homework problems they call them? So these are solutions to practice problems. Yeah, homework problems. So I'm just gonna call it problems.txt. And this is gonna be practice. Maybe we'll do this as a markdown. Yeah, sure. MV problems to problems MD. Problems. 1.1. I'm gonna do A. Okay. You hear on the news that Montana has a okay, so this is like, let's get the facts here. So distance is equal to 2,500 km, and speed is equal to 100 km per hour. Up here we'll just type in the Amdahl's law. S is equal to 1 over actually, let me see if I can remember this just off the top of my head without looking at it. S is equal to 1 over 1 minus alpha plus alpha divided by k. Yeah, okay. So A would be taking this expression here, and it's asking what will your speed up for the trip be. So we're going to say that alpha is equal to how many kilometers? 150 km. But alpha is expressed as a coefficient of 1. So we have to say, okay, it would be 2,500 divided by km divided by 100 km. So let's just do another little Python thing down here. We say 2,500 divided by 150. So that gives you 16. But if you want to map it into a range between, so it'd be, to express this as a cross multiplication relationship equation, you would say 2,500 divided is to 1, as is 150 is to x. So then you get the equation 250,000x is equal to 150. So to isolate x, it's actually 150 divided by 2,500. So it's the inverse of this, which is what I thought. So instead of being 16, it'd be 1/16. So alpha is 150 divided by 2,500, which is a very small amount of the trip. It's not even, how's that? Do I need to times it by 100? No, because 0 to 1. If I do times it by 100, this will give you by a percentage. So it's like 0.6%. That is like so small. That's not possible. Let's go back here. I messed something up. So you have 2,500 is 1. So 150 is X. If we did something like, oh, I forgot a 0 on here. That's right. Okay, that would explain why. So A is equal to 0.06. That's a little bit more realistic. And K is equal to the speed up of that. So that would be, the speed up is 150 miles an hour. Yeah, 150 miles an hour. So we have to say 150 is X times our original, which is 100. So it'd be 150 divided by 100. And I'm just going to drop the units here because it's just a lot of typing. So 150 divided by 100 would be 1.5. Speed up. So K is equal to 1.5. So here we substitute in 1 over 1 minus the 0.06. It's not even a significant amount of the trip. Plus A divided by K, which will be 0.06 divided by 1.5. So then that will equal to 1 divided by, actually I'll just evaluate this here in Python, bam. So this would be 94, 0.94 plus this little bit, 0.04, 0.04, and if we do just parentheses around this, like that, we could just give this to Python and have it evaluate it. Bam. There we go. So speed up is equal to basically 1.2. So that's A. B, you could buy a new turbocharger for your truck at fasttrucks.com. They stock a variety of models, but the faster you want to go, the more it will cost. How fast must you travel through Montana to get an overall speed up for your trip of 1.67? So this is where we have to reverse the equation. So let's go ahead and grab the equation here. So we already know S is equal to, so we have to solve for the speed up coefficient over here, which is K. So here we're going to say A is still equal to, is it still 150 miles, right? No, it's 150,000 kilometers. Okay. No, 1,500 kilometers. What? Okay. So my math was just totally wrong here. Let's go ahead and go back to this. I just typed it in wrong here. So it's 1,500 kilometers a trip. Your truck travels at, okay. So then this is now going to be this. Sorry, I forgot a comma in there. 0.6. Okay. Which takes this down to this. And then if I yoink that off, 0.4 And if I yank this off, it's still 1.5 for K because it's still 150 kilometers an hour. And our current speed is 100 kilometers an hour. Yeah. Okay. So it's basically 0.4. And then if I evaluate this whole expression here, that'll give me the correct answer, which is 1.25. Okay. Alright, so now we go to B. Glad I caught that. So we go down here. Our A is still the same. I'm just going to leave that like that. K is unknown, and our S is equal to, it says right here, we want our S to be 1.67x. So we just got to work this expression here. So you say, copy that, 1.67 is equal to 1 over 1 minus A, which is 0.6. And then this is 0.6 over K. And we're solving for K. So the first thing I'm going to do is, well, I got to space this over here. We'll evaluate this into 0.4, and 0.6 divided by K will leave. So what we're going to do is multiply both sides by this term. So now it becomes, oops. So basically we can flip this term here into this, but then we have to put this under 1 divided by that. Okay. And that allows us to do away with this. And now we can say that minus this term. Actually, if we just do 1 divided by 1.67, and we'll preserve this expression here until the very end in case there's some floating point rounding errors. So this thing goes to be minus that. Oops. Come on. Okay, so that takes off of this. And now we can do the same thing where we isolate K. So normally we would multiply both sides by K to put K on the left-hand side. But then we would have to divide both sides by that expression. So really what we're saying here is that K is equal to 0.6, because that's not moving, divided by this. And we invert it because of the 1. So K is equal to this expression. And if I plug that in here, wait a minute, that's wrong. That's me doing the arithmetic myself. If I just implement this as a function in Python, we'll say def s is equal to, it takes in a and k, sorry, a and k, and returns this expression here. I'll have to replace some things. Return that expression, but I need to replace that and that. And we'll use floating point division, that's fine. So now if I say S of 1.25, sorry, we have A and K as 1500 and K as 150. So something's wrong here. Is it precedence? Sorry, A is equal to 0.6. 0.6, I got these things wrong. And K is equal to 1.5. There you go, 1.25. So the first one's correct. If we say here that a is equal to 0.6 again, but k is equal to, what did I get? I don't know. It needs to be like something like 3, right? Yeah, it needs to be a number higher than that. So something's wrong with my algebra here. All right, so let's take it from the beginning. 1 minus a over k. That's correct. Put in 1.67 because that was our target. And 0.6 still goes there. 0.6 goes there. This 1 minus 0.6 is 0.4. Just verify that. Boom. And then 0.6 divided by k. We have to preserve that because we don't know what k is. So we get down to here. That's correct. So everything's correct down to here. And now we say, okay, how about we do it the traditional way? So we multiply both sides by this term to get it out from there, which turns it into that. So again, we're trying to isolate k. So that means that we divide both sides by this. So that is correct. This is correct. It's just on the wrong side, which is fine. And then we subtract off 0.4 from both sides. Precedence is correct on the left-hand side. That leaves 0.6 over k. And now we do the same thing where we take a, we're going to multiply both sides by k. So k goes over here, k comes out from there, and now I have to divide both sides by this expression here. Divided by, oh, I lost a 1 here. Yeah, this needs to be a multiplication. So the 1 gets lost, but it turns into a multiplication. That's where I messed up. And this needs to be, oh wait, we can't do that. Because if I do this, this has higher precedence here. So what we need to do is just evaluate this here. We'll just evaluate the whole thing. They're all like that. Okay, 3 point k is equal to, it'd be nice if it didn't do that, 3.02 basically. And we can verify that by calling our s function and saying, hey, a is 0.6 and k is 3.02. What do we get at the other end? 1.67. Yep. Okay. Some basic algebra there. It's good practice. Okay, so that's practice problem 1.1. There's an aside here. The best way to express a performance improvement is a ratio of the form T old divided by T new, where T old is the time required for the original version and T new is the time required by the modified version. So if T old was like 100 seconds and T new is 50 seconds, you get a 2x speed up. Where T old is time required for the original, T new is required for the modified version, this will be a number greater than 1 if any real improvement occurred. We use the suffix x to indicate such a ratio, where the factor 2.2x is expressed verbally as 2.2 times. The more traditional way of expressing relative change as a percentage works well when the change is small, but its definition is ambiguous. Should it be 100? Yeah, exactly. There is a difficulty in that. Should it be 100 times T old minus T new divided by T new, or possibly 100 times T old divided by T new divided by T old, or something else. In addition, it is less instructive for large changes saying that performance improved by 120% is more difficult to comprehend than saying that the performance improved by 2.2x. Yeah, because it's like, did you add on that 120% to the original 100%? Or when we say, or is it adding on 20% to the original 100%? Yeah, I get what they're saying there. All right, practice problem 1.2. It is, we got 15 minutes, okay. Car manufacturing company has promised their customers that the next release of a new engine will show a 4x performance improvement. You have been assigned the task of delivering on that problem, so that's great. You have determined that only 90% of the engine can be improved. How much, i.e. what value of K, would you need to improve this part to meet the overall performance target of the engine? Okay, just another application of Amdahl's law. So 1.2, and we'll grab Amdahl's law here, and we'll say, hey, we got S is equal to 4, and A is equal to 0.9. So we're going to do the same thing here. We put 4 here. Oops. Let's do 4. And this will be 0.9. Put 0.9 here. This evaluates to 0.1. And A divided by, we'll leave A over there. So now we gotta like take a, multiply both sides by this term. So now this gets over here. And this comes over here. We can remove these brackets now. We need to now, oops, subtract off this term. There, goes over here. Precedence remains unchanged. So now we have A divided by that. We now need to multiply both sides by that. So this thing comes over here, and we say, hey, you go over there with that. And then we can just say A is equal to the evaluation of this expression. Boom. So A, wait a minute, A. Did I do that wrong? I did that wrong. Yep, I did that totally wrong. Divided by K, we don't know K. We're solving for K again. Alright, let's do this again. So this thing, well, first of all, this turns back into 0.1. And then this whole thing gets multiplied over here. So these things trade places. Come on. So this goes over here, and then 4 goes over here. And then we can drop these, and then subtract off 0.1 there, which gives us this. Okay, precedence still works, okay. So now we need to multiply both sides by K again, which puts K over here. K times this. And then that needs to be divided. So now we take this guy and put him over here. Let's do a little swapperoo. And we can take K and bring him over here. K is equal to that. Okay. So now we can evaluate this. And this should be the right value for K. 6. So K is equal to 6. And we will space this in here appropriately. Like that. Let's do something similar here with that and this. There we go. And we can verify S of 0.9 and 6 will give us the 4x that we want. Yep, cool. Okay, let's go ahead and just check our solutions here. So at the end of the chapter should be solutions. This problem illustrates that Amdahl's law applies to more than just computer systems. So here's A. In terms of equation 1-1, we have alpha 06, yep. K is 1.5. More directly, traveling 150,000 kilometers through Montana will require 10 hours, and the rest of the trip will also require 10 hours. This will give us a speed up of 1.25x. And then B, in terms of equation 1-1, we have alpha 06, and we require S to be 1.67, from which we can solve for K. More directly, the speed up of the trip is by 1.67x. We must decrease the overall time to 15 hours. The parts outside of Montana will still require 10 hours. So we must drive through Montana in 5 hours. This requires traveling at 300 kilometers an hour, which is pretty fast, which is 3x our original, yeah, I'll just say 300 kilometers per hour. 3x our original, basically. And then 1.2, Amdahl's law is best understood by working through some examples. This one requires you to look at equation 1-1 from an unusual perspective. This problem is a simple application of the equation. You're given S and A, and you must then solve for K. Yep. Which is X. All right, let's continue reading. One interesting special case of Amdahl's law is to consider the effect of setting K to infinity. I've been doing this. I did this in the video I recorded yesterday. That is, we are able to take some part of the system and speed it up to the point at which it takes a negligible amount of time. We then get S infinity is equal to 1 over 1 minus A. Yeah. For example, if we can speed up 60% of the system to the point where it requires close to no time, then our net speed up is still only be 2.5x. Amdahl's law describes a general principle for improving any process. In addition of its application to speeding up computer systems, it can guide a company trying to reduce the cost of manufacturing razor blades, or a student trying to improve his or her grade point average. Perhaps it is most meaningful in the world of computers, where we routinely improve performance by a factor of 2 or more. Such high factors can only be achieved by optimizing large parts of the system. Concurrency and parallelism. Oops, sorry, I'm on the wrong page here. Boop. Throughout the history of digital computers, how much time do I have? 4 minutes. How about we just take a break here? It'll give me time to get ready for my dentist appointment, and then I'll come back and pick up on concurrency and parallelism. Yeah, let's do that. Cool. I will be back after lunch. I'm going to go to the dentist, eat lunch, and then I'll be back on until this evening. Cool. All right. See you then. Bye.